Hello everyone, this is Doug, and so for this video, we're going to talk about the alpha halogenations, right? So if I want to put a leaving group on there so I can do more chemistry, how do I get a halogen into that alpha position of a... So what do we mean by alpha halogenations, right? Of course, alpha we mean one away from the carbonyl. And halogenations, we're talking about any of the halogens, right? So fluorine, chlorine, bromine, or iodine. The ones that you see the most are probably chlorine, and actually, that's not true. Not chlorine. Just kidding, just kidding. The ones that you see the most are bromine and iodine because they are the easiest to handle, right? Fluorine is just super toxic in a gas. Chlorine is toxic and a gas, but at least bromine is a liquid and iodine is a solid. So those are just more easy to work with, and they're great leaving groups once you put them on. So you tend to see a lot of those. But regardless, the point is that you, in that alpha position, you're going to replace one or more hydrogens with the halogen that you were looking for, right? So now you've got more functionality. You can do eliminations and substitutions and things at that point. So let's take a look at the acidic conditions first real quick, just an overview. If you have acidic conditions or neutral conditions, right, so I just need to add any amount of catalytic acid. Notice it's just a catalyst because we're going to remake this. The idea is that if you take a look at this, your alpha positions, right, here I have two alpha positions on my starting molecule. The hydrogens there are going to be more reactive because of that enol or enolate intermediate, right? And so what we see is that only one gets replaced. Only one hydrogen gets replaced. That's different than in the basic conditions, right? So if I look at the basic conditions, what I'm going to see is that with the basic conditions, I need molar equivalents, right? I need however many halogens I'm going to rip off, that's how many OHs I need at least. Usually we do excess, so I need molar equivalents, right? Not just a catalyst. This is not a catalytic amount of base. This is stoichiometric, large amounts of bases. And it's the same molecule as the one above here, right? So again, if I look at this alpha hydrogen spot, this alpha carbon, I have, looks like 1, 2, 3, 4 alpha hydrogens. All 4 of those hydrogens get removed and you replace them with whatever halogen. Again, I chose chlorine in this case. It would be the same thing if it was bromine or iodine. The idea is that all of them get replaced, right? So the key for when you're in basic conditions is that all of the alpha hydrogen atoms get replaced. And we'll see why in the mechanism in a little bit here. So under the acidic conditions, right? So let's look at the acidic conditions here for this alpha halogenation. It's going to proceed through the enol, and that's what we'll see in the mechanism in a second. And like I said before, it only replaces one of those alpha hydrogen atoms. And let's take a look at the mechanism so we can kind of see a little bit better why here. So I'm going to draw out my chlorine, my Cl2, just so we can see it. And then I've got my H+, right? And if I put my partial charges on my ketone, partial negative, partial positive. First step here, right, anytime you have a catalytic amount of acid and a carbonyl, almost always the first step is going to be you protonate the carbonyl, right? You're trying to make the carbonyl more reactive for some reason. Because just chlorine and the carbonyl may or may not react. It kind of depends on the temperature and it depends on the concentration. So the acid is there just to speed it up, right? It's a catalyst. It's just there to speed it up a little bit. Technically, you don't need it. I'll show you an example that I did with the bromination where you don't really need it. But with chlorine, I'm going to go ahead and show you one with the acid catalyst. So I'm going to go ahead and protonate, right? So I'm going to go ahead and protonate my carbonyl. Now the idea here, right, so reversible reaction, the idea here is that protonating your carbonyl makes it more electrophilic, but I don't really have any nucleophiles, so that's not the concern. But the reason we're doing this is because it's more likely, or you're going to be able to form a little bit more enolate than if you, or sorry, more enol than if you did not have it. So what you're going to see here is that in these alpha spots, and I'll do it on the right-hand side, right? I had this alpha position, this alpha. Oh, I'll do it on the left-hand side, actually, since that's where I put my chlorine. What you have happen is in acidic conditions, carbonyls tend to form a little bit more of the enol because of this, right? So I'm going to draw the hydrogen. In order for me to, or one way that I can let that let that oxygen get its electrons back is to remove the hydrogen, which is going backwards. Or what we can see happen is that the alpha hydrogen can drop down, kicking the pi electrons back up onto the O, so that now there's a double bond here and an O. The oxygen gained back some electrons, so it's no longer charged, and now we have an H. And you'll notice, right, that we have formed the enol. So that's what I mean about going through the enol here, right? Here's my enol. This is a very small amount, right? This is very slow. There's very little of this. But when there is some of this, the idea is that now the enol, right, is a little nucleophilic, right? Remember that enols have that resonance structure that I can draw, where I can have those electrons drop down to make a double bond here, like too many electrons on that oxygen, thank you, and put the negative there, right? So it's just the tautomerization here, right? The enol, this is what the enol looks like. But that means that alpha carbon now is slightly nucleophilic, right? So I'm going to say the alpha carbon is now nucleophilic, which is great, because now that means that I can go and attack something like a halogen, like Cl2, Br2, I2. I can go attack something, and that's exactly what we see in this next step. Again, with resonance structures, it doesn't matter which one you pick to go attack the chlorine. I like picking the one where the negative charge really is, because I think it's super apparent that way. So I'm going to attack one of these chlorines, break that Cl, that weak Cl-Cl bond, which is going to give me, right, a nice stable chloride. And what I have now is double bond O, there's an H, got a lone pair and a positive charge. I forgot the positive charge back there. And now I have a chlorine attached to my alpha spot, right? So I've done the alpha halogenation. And then the last step here is just for my carbonyl to lose its hydrogen, right? To go back, to go back to the product. Plus H plus, and right, so we regenerate the H plus, which is why we just need catalytic amounts of it, but we've added a chlorine onto it. Now, what I want to point out here is that, again, this only replaces one alpha hydrogen. And that's because as soon as you get one alpha hydrogen on there, and let me draw this at the bottom here. As soon as you get one alpha hydrogen on here, or sorry, one alpha halogen on here, the idea is that the enol that would be formed here, right? So let's say we have this enol. The chlorine, if you remember, right, the chlorine is an electron withdrawer, right? So it makes the alkene less electron rich, right? Chlorine, so now this alkene is less electron rich, which means, right, you should be asking yourself, well, so if it's less electron rich, is it more nucleophilic or is it less nucleophilic? In this case, right, if it's going to be less electron rich, it becomes less nucleophilic, which means the subsequent halogenation is going to be slower. And so it becomes worse and worse and worse of a nucleophile every time you try to add a halogen to it. And so it just doesn't halogenate very much at all, right? It makes this step really slow. Makes this step really slow. So we don't see it halogenate a whole bunch of times, because as soon as you put a chlorine on there, it pulls electrons away from the alkene, and now it is no longer as nucleophilic. So it's not going to attack another equivalent of Cl2. It's just not going to. We just see monohalogenations when you're in neutral or acidic conditions. Now we'll see how that's really different for basic conditions. So for basic conditions, right, alpha halogenation, we got basic conditions, we're going to proceed through the enolate. So we're flat out going to deprotonate and make an enolate, right? Notice again in that previous slide, we had the enol. I never had the enolate. I never had something that was fully negative. And what we're going to see in this one is it's going to replace all of those alpha hydrogens. They're all going to get replaced. And again, we're going to see why here in a sec. So I'm going to go ahead and draw out my reagents a little bit more here, right? So I've got my Cl2. And I've got my sodium hydroxide. So I'm going to go ahead and split my sodium hydroxide apart, right? Because it's an ionic compound. So just go ahead and dissociate it. And if I take a look here, right, again, chlorine's not nucleophilic. It's not going to go attack my carbonyl. But I do have a base. And right, remember we said that these alpha hydrogens here are a little acidic. And what we're going to see here is that while hydroxide is not a great base for deprotonating alpha hydrogens, it's not going to fully deprotonate. It'll do just a little tiny bit. It's enough to get this reaction going and to get us started. So I'm going to have a hydroxide take off one of these alpha hydrogens. And I'm going to draw this equilibrium arrow like this, right? This is really slow. This is not a very high yield. This is not a good equilibrium. And again, I'm going to draw the resonance structure just to emphasize here why those alpha hydrogens are relatively acidic, because you've got this resonance structure. But once again, right, the idea here is that now this is nucleophilic. So now the alpha carbon is nucleophilic. And so now this is able to go and attack that Cl2 like we were talking about before, right? So now this can go attack a Cl2 and kick out the other chloride, giving us our product. And the Cl minus. And well, let me just stop there, right? So that's how you get the product with one chlorine. Now, what we want to remember here is that we said that there is an excess of this stuff. We have lots and lots and lots of hydroxide. So what's going to happen then if I have more hydroxide hanging around here? Will this hydroxide react again? Will it deprotonate another hydrogen? And like we said before, right, the chlorines are electron withdrawing groups, right? They withdraw through induction. And so if I take a look at, well, what if we do remove a second hydrogen, right? There's a second hydrogen here. If I have a second hydrogen here and I imagine trying to take off that second hydrogen, I'm going to form again an enolate. There's a chlorine, but now there's a lone pair here and a negative charge. Now I have this chlorine that's taking away electrons, right? It's a weak electron withdrawing group. It's just very electronegative, so it's going to withdraw some electron density. We have to ask ourselves, is that helping or hurting this anion, right? So I've got a negative anion. I'm pulling electrons away. Let me write this down. So the halogen is electron withdrawing. Which means it is going to stabilize the anion. Right, because the anion had too many electrons, right? That's why it's negative. So if you pull electrons away, that makes it more stable. So it actually stabilizes the anion, which makes the alpha hydrogen more acidic. Right, so now it made this alpha hydrogen right here more acidic. That's a more acidic hydrogen now than one of these up here was, right? One of these up here. When you had just your parent carbonyl, there were no halogens on there. You took off a hydrogen, but as soon as you get a halogen on there, now it becomes more acidic. And so this reaction is able to happen again, right? Where I have another equivalent of Cl2, or again, again, it could be Br2 or I2 or something else. But this can then go and attack another chlorine. It's like not even close to an arrow. Another chlorine. And then you get a second halogen on that alpha spot, right? Plus another chloride. And so you can imagine what keeps on happening. The more chlorines you get on there, the more acidic these alpha hydrogens become, right? I know that the chlorines aren't at the same alpha spot, but they're still going to have an effect even if it's 2 carbons over. So it makes those other alpha hydrogens more acidic than the ones at the very beginning. And so this just keeps on happening until there are no more alpha hydrogens, right? So you just keep on removing alpha hydrogens and adding chlorines until you get to the product. Because every time you add a halogen, the remaining alpha hydrogens become more acidic. So it just keeps on going. You replace all of the hydrogens. That's why you replace all of the hydrogens here. So let's take a look at applying some of these here, right? What are these products going to look like if you just asked, well, this plus this makes what? And so here I have Br2. I see that I have basic conditions, right? I have a base, sodium hydroxide base. So that means I'm going to replace all of the hydrogens with bromines. So if I look at this, right, again, I have 2 alpha spots in this case, 1, 2. So I'm going to replace all of those suckers with bromines. Br, 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 right? Because we're in basic conditions, replace them all. Because every time you put on 1 bromine, that product becomes more acidic than the starting material, so you're just going to keep on brominating. Here, in the second one, I see that I just have bromine, so this looks neutral, which means I'm only going to do 1. I'm only going to put on 1 halogen here. So double bond O, I'm just going to put on 1 Br. I have 2 alpha spots, but only one thing has alpha hydrogens, right? I have an alpha carbon here and an alpha carbon here, but I don't have any alpha hydrogens on that T-butyl group. They're just all methyls. So I got to put the bromine on the right-hand side. And then, well, let me draw those hydrogens out here just so that we're on the same page, right? I only have, right here's my only alpha hydrogens. No alpha hydrogens on the left. And then lastly, down here on this one, it looks like, well, if I take a look at this, I have more than 1 chlorine. All right, so I have many halogens. And so therefore, it must be under basic conditions. So I'm just going to put Cl2 because that's the halogen, and then basic conditions, you can just use hydroxide. Really any base, but hydroxide is super common. So that's how I'd approach these, right? Just look at how many halogens are on there. How many do you want on there? Now, how do we apply this in a synthetic sort of scheme? How do we want to like contextualize this? Why would we even bother doing alpha halogenations? So here's 2 examples of syntheses that involve alpha halogenations. You have to do an alpha halogenation. I recommend that you pause, take a crack at this, and see what you can do. All right, I'll pause for, I'll stop talking for a second. So hopefully you had some thoughts here about how to approach these syntheses. If I take a look at this molecule here, right, for the top one, I notice that I have an amine, 2 spots, 2 places, 2 positions from my carbonyl. Or in other words, right, 2 spots away is another way of saying a beta, right? It's beta from the carbonyl, which makes me think maybe I need to do some sort of conjugate addition, you know, that 1,4 addition. A conjugate addition, right, or that 1,4 addition. And I know how to do that, but I know I need an alpha-beta unsaturated system, which I don't have, right? The starting material is not alpha-beta unsaturated. So maybe I need an alpha-beta unsaturated system. And which means I need to make an alkene. I need to make an alkene. And I know how to do that. I know how to make alkenes from E2 reactions. So what I'm going to do then is I think I'm going to go ahead and I'm going to do an alpha halogenation. Let's do an alpha bromination, right? So let's say I'm going to add Br2 and acid. So let's just say acetic acid. So CH3CO2H maybe. So I have some acid. Now that should give me just one bromine, right? Because it's just acidic conditions, it's just one bromine there. But once I have a halogen there, I can do my substitutions, I can do my eliminations, I can do all of those sorts of things, right? So now I think I'm just going to go ahead and add a base, and I'm just going to play it safe and use a big bulky base because I know that they're not going to substitute out. And if I do that, then my big bulky base is going to give me an alkene down there, right? I have hydrogens to do eliminations on the right-hand side clockwise for the bromine, but not the other direction, right? So let me write that out. What I'm saying is for this one, for the LDA, I only have halogens there. So the LDA must attack those to do my elimination. So now I've got my alpha-beta unsaturated system. Awesome. I know how to then convert this into that. All I really need to do is add the amine that I wanted, and then a catalytic amount of acid, and that should give me that product, right? So I can do my conjugate addition. So here's an example of, you can use alpha halogenations to make yourself an alpha-beta unsaturated system. You can do a elimination. You also could have done a substitution here, right? I could have taken that alpha-bromo thing and added, any nucleophile really that you want, and you could have put it there in that alpha spot. Now, if I take a look at the one below, let's see, we have more carbons. Right, we have more carbons. We have a new CC bond. Actually, it's a CC double bond, new CC double bond here, right? And if I take a look at this, it does look like this alpha carbon is the point at which it got connected. And I see a new CC bond, which makes me think that maybe this is something like I used an alkyne, but that doesn't work because then the double bond's in the wrong place. Maybe I used Wittig. Could have used a Wittig. Maybe I could have used a Grignard. Grignard reagent, some organometallic reagent, to make that CC bond. But I think the simplest way here is going to be with the Wittig. That should be the fastest. So I need to somehow make an ylide, right? Because if I look at this molecule, if for example, if I had this ylide and benzaldehyde, that would give me that product. That's what I'm looking for, right? It's a stabilized ylide. It should give me the E alkene, right? The trans one that's more stable. But I need to turn my parent carbonyl, right? This methyl isopropyl carbonyl, or in other words, the 3-methyl-2-butanone. I need to turn that into the ylide. So I need to get the triphenylphosphine onto that alpha spot. How do I get it to the alpha spot? Halogenation. So I'm just gonna, I actually did this reaction in my research, right? So I just took a whole bunch of bromine and I plopped it in all at once because that's what the prep told me to do. And the main product I got out of it was this, right? Where I added the bromine to the less substitute of the two. That would be your kinetic product, which is why you need to add everything all at once really quickly. If you add it dropwise, you end up getting the bromine mostly on the other side because it has time to equilibrate. But in this case, if you just add a whole bunch of bromine, boom, it goes in that alpha spot. And then now that I have that bromine there, I know that I can add the triphenylphosphine, pH3, right? This is just making the Wittig. This is stuff from that Wittig video. pH3. And then to turn it to an ylide, all I really need for this is I just need to add hydroxide because it's a stabilized ylide. You can just add pretty much any base. and it will deprotonate that hydrogen here, right? You have this hydrogen here that it's going to deprotonate. Come on, friend. Go back. Okay, I'll just erase you. There we go. Sorry, my computer's not listening. There we go. Right, so the hydroxide would just take off one of these hydrogens to give you your alkene. And that would give you the product. Right, so here's two ways that you can use those alpha halogenations in a synthetic scheme. You know, maybe you want to do a substitution at the alpha spot, like the bottom one. Maybe you want to do an elimination to get an alpha beta unsaturated system, like in the top one. So anyways, I hope that gives you a better sense of what the alpha halogenations are like. Do lots of practice, happy studying, and good luck.